Hello and welcome back. We now discuss how we can use regression tasks in machine learning. So first of all, what are regression tasks? Essentially, this is about curve fitting. We have a bunch of data points that we want to associate with a numerical value. So we start with our data, with our random variables x1 and so on, and we map this to our target value. So we call the y hat the dependent variable, the target, the label, and what the model does is that we make a prediction for this quantity, and this prediction is indicated by a little hat. The x are the independent variables, or our features or feature variables, and our model is the function f that depends on those variables x1 to n, and they also depend, at least in general, on some parameters. And this function describes the relationship or the mapping between the feature variables and the target variable y. The simplest case for regression is called the linear regression. So here the function is a linear combination of all the features. Essentially, our predictor, the y hat, is the sum of all the feature variables, and we modify this with a single coefficient. Essentially, this is a straight line fit for all the data points across all the feature variables, and if you only have one variable, you can literally get the familiar one, y equals mx plus b. We perform the fit by minimizing the residual. This is our loss function. So what we want to do here is we have the true labels, these are our values y, and we have the model output y hat. And the error between the two of them squared, this is our residual, and we want to minimize this. So that means that the least square fit should describe the true value as well as possible. This is essentially a least square estimation. What are the advantages of this? So it's very simple, both conceptually but also computationally. It's quite interpretable because the coefficients give us an indication which feature contributes how much. So it's a good baseline for any more complex, and any more complex model should be able to beat this. The disadvantages are, of course, we don't take the correlation between the variables into account. All variables are treated as independent, and also we don't model any non-linear relationships. The whole approach is quite unstable with respect to outliers. As you can imagine, if you have a point cloud of data points that are close to each other, this works quite well, but if you have a large variance, but if you also have a cluster or a few single points that are far away from the bulk of these data points, they will also be considered with the same approach than all the other data points, and this can have a big impact. So in the end, it doesn't take all information into account. The extension is to do nonlinear regression, and we can do this, for example, by allowing nonlinear relationships, for example, higher order polynomials. Here the obvious question is how many terms should we have? If we have too few of them, we might not have enough flexibility to fit the data we have. If we have too many, of course, we are prone to overfitting, and we fail to capture the essence of the data and start fitting the noise. To estimate this, we need to understand what we mean by underfitting and overfitting. The expectation is, at least in general, that there's a smooth curve that describes our data, and the fit result should describe the data well enough but not too well. So what do we mean by this? On the left we see an underfitted result. It's a very simple straight line, but we can see that it doesn't really capture what the data looks like. On the other hand, on the right, we see that the fitted curve has a lot of wiggles, and we don't really expect this to happen either, because there is probably some noise in the data. So we expect that whatever we fit will go through those points, but not through every single point individually and exactly. How can we make our model more robust and prevent, for example, overfitting? And one approach is regularization. The key idea is that we have a more flexible model with many parameters, but we penalize using this flexibility. So remember before, we had the least squares estimation from the linear regression, where we compared the true value y with the prediction model, and in the case of linear regression this was just the sum of the features with the constant, and this is our y hat. And the fit was done by minimizing this residual. Now we add a regularization term. So we have a new free parameter, the strength term, lambda. Now obviously if lambda is 0, we get back our unconstrained result, and the stronger or the larger value lambda takes, the more important the regularization will be. Now we add some penalty term, and then we follow the same procedure. We minimize, but instead of just minimizing the residuals, we now minimize the residuals plus this penalty term. So far so good, but what is the penalty term? There are two main approaches for this. One is called lasso, least absolute shrinkage selection operator. This is essentially penalizing the absolute value of the parameters A. So it's a linear penalty and has the advantage that it favors sparse models because the A can go directly to 0. Implicit in this method we have a feature selection one, so all those variables that don't contribute too significantly, they will be regularized away. The other one that is frequently used is ridge regression. This is a quadratic penalty, and that is good for many correlated features. Of course, we can also combine the two of them. So if we do this, we have our linear regression with a high degree of flexibility in the top left one, and now we add the penalization. You can see from the two results that the ridge and the lasso regularization perform slightly differently. And you can also look at the regression coefficient. For example, in lasso we see that most of the features, or in this case the data points, are taken to a very small value, and we only have very few. This is this implicit selection of features, whereas for ridge regression we have a larger variance. Of course, simple regression is not called simple regression for nothing. It is really a fit of a straight line, the simplest model we can have. The assumption is that the true model is just a straight line and the variance and the volatility is just due to noise. And what we essentially do, we do a linear regression on the mean. But of course we already know that variables follow a specific probability distribution. Here, when we do simple linear regression, we estimate the mean, but then we don't capture the essence of this distribution because it's not really sufficient. This is particularly true if we have asymmetric distributions, like for example the Wildwood distribution. So what we can do, for example, is do quantile regression. In approach 1, where the underlying probability density distribution is known, we build a regression model for the parameters of this PDF for the individual models. The other approach is to do quantile regression itself. This is similar to linear regression, but now for specific quantiles. Remember that we just said earlier that the standard linear regression is associated with a mean, and here we extend this to capture different quantiles, and this is illustrated on the right. So depending on which quantile we take, we get something that is close to the simple linear regression, especially for symmetric distributions, but we can also capture the variance with different quantiles. So to recap, in linear regression the mean is our estimator, and in quantile regression the quantile is our estimator. Now the key question is, which quantile do we want to use? And again, there is no one-fits-all answer. For example, if you were to operate a supermarket, you would want to have a high product availability of all your products. So there you want to have a high quantile, so the products you sell are almost always available. However, if you are an engineer and focus on predictive maintenance or reliability engineering, you really want to have a low quantile because you want to estimate a low probability of failure. So you really need to understand your application domain to be able to make this judgment. You can also extend linear regression to generalized additive models. The linear regression has the advantage that it's very simple and easy to understand, and it's also explainable because the strength of the parameter A are related to the importance of the features. This is often a good baseline, as we said, but it's not very powerful. Generalized additive models extend the linear regression and show good performance in many applications, and they're mostly explainable as well. And you can see on the right hand side how the formula gets slightly more complex. On the top we see the equation for the simple linear regression, and on the bottom we see the one for the generalized additive model. So the general structure is the same, just becomes slightly more complex. Instead of the features x, we have now a function that uses those as input, and we use the result of this function. We can also add pairwise interactions by having a function that operates on two of the features simultaneously. And we also don't predict the target directly, the y, but we work on the expectation value and in a different function space with a link function g. But the concept is still pretty much the same, but the power of the generalized additive models comes from the increased complexity of working with the different functions inside the definition.